Our last speaker is Niema Moshiri. He's from UCSD and going to talk about HIV epidemiology.
Perfect. So yeah, as she mentioned, I'm from UCSD. I study HIV epidemiology, but more from an algorithms background. So first, just some background information on some common problems that we have in HIV. So first, HIV is thought to have been introduced in the US in the 1970s, and its spread is driven by social and sexual networks. And it's very maintained in the Western world in that if someone has HIV, they can come to the clinic and receive treatment. But in sub-Saharan Africa, it's extremely rampant. There's no actual cure, but there are antiretroviral therapies that you can basically, if you adhere to this medication, then you can be effectively asymptomatic. It's just a matter of, it's not a cure because if you stop the treatment, then the virus typically comes back. So in the US, also upon receiving ART in the clinic, the viral sequence is also typically obtained. So now we have these very nice, robust databases of viral sequences. And from a phylogenetic context, in general, upon infection, there's a single founder virus. And if you look at the global tree, there's generally many short internal branches with very long leaves. So this type of tree, for reasons I won't really go into, they're typically hard to infer phylogenetically. And from a molecular background, there's high initial sequence diversification upon infection. And at the genome level, the virus is very highly recombinant. But at individual gene levels, it's typically very conserved. So if you were to only look at a single gene, which currently most people usually only look at the POL gene, polymerase, or the GAG gene, or some complex of the two of them, because these are protein coding genes, usually this assumption of recombinance, you can kind of like throw that out, which helps simplify the problem a bit. And then if we were to zoom out a little bit and try to take the entire epidemic as a generative process, you can think of one stage of it being the contact network, which is just this superset of all possible social interactions that people have. And then subject to that is the transmission network, which is the actual transmission events that happen. You can think of this one as a directed subgraph. The math notation got a little bit messed up, but it's OK. And then dependent on that is the actual phylogenetic tree and the sequences, which you can imagine are dependent on the transmission history. So I'll get more into detail about these things in a little bit, but basically we can summarize the raw input as we either have whole genome or individual gene sequences. You can get it from Sanger sequencing, which will generally get you a consensus sequence of your entire viral population, or you can get high throughput sequences, which will give you individual fragments. And we typically also have sample times from each individual. So the first kind of general question that I want to pose is, given sequences obtained at known times, can we infer the viral phylogeny and transmission network? So phylogenetic inference on its own, it's a very well-studied problem, and it's a challenging problem. So currently, maximum likelihood methods are typically considered to be the best to use. However, we show, for reasons that I won't really go into detail right now, that the types of trees that you would get, that you would expect with HIV are actually very hard to infer with maximum likelihood errors. And we typically see roughly 40 to 50 topological error, 40 to 50%. And then further, dating and rooting these trees can be difficult. Another difficulty, if you were to try to use these phylogenetic histories to try to infer the transmission histories, you can kind of think of the transmission history as a species tree, if you're in that realm, where basically we have this transmission history of a blue person maybe infected the green person at that initial top time, and then the green person infected the purple person, green person infected yellow person. One form of the viral phylogeny will kind of correspond to this, it won't be discordant against this transmission tree, versus we could also have some examples where the viral lineage actually opposes the topology of the true transmission history. So we have difficulties that you would see in other fields of phylogenetics as well. So some problems that people, some ways that people try to approach this problem is via transmission clustering. So given a bunch of people, can we see which individuals are more likely infected from the same source? Usually they have distance-based methods dependent on either sequences or phylogenetic distances, and I list a few here. And they try to use these transmission histories, these transmission clusters to predict other features. For example, can we use these to try to can we predict future transmissions using these inferred networks? So in the context of HIV, we can kind of think of the number of infected people in each population as this type of sigmoidal curve where when it's first introduced into a community, it rapidly grows, and then eventually you hit this kind of slowing down pace. So if we have these transmission clusters, can we try to predict which communities are the most at risk? So which ones are kind of in this exponential stage of the sigmoidal curve? And we show in some of our more recent studies that you actually can use these cluster growth, you can use these transmission clusters to try to pick people for intervention, and they do significantly better than random. But they don't do as well as we theoretically could. So in this figure, I show a green line as the optimal theoretical limit of how well we could do. So there's significant room for improvement in terms of intervention using these methods. And the last question that I kind of want to pose is, can we also now use mathematical modeling to simulate realistic sequences? So if we want to study epidemic outcomes, there's this kind of big question of, as a public health official, should I invest more money in spreading treatment, or should I invest more money in intervention or prevention? So using mathematical modeling, we can kind of hone in on these questions and see, if I increase the rate of this phenomenon, how does the outcome of the epidemic get affected? And then also, these transmission clustering and transmission inference tools, we can't really figure out how well they work unless we use simulation to test that out. So in a recent paper, we've introduced a very general framework for simulating viral sequences. Basically, we treat every stage of an epidemic, and the numbers got kind of messed up, but don't worry about those, I guess. But we treat every stage of this as some probabilistic distribution dependent on all previous stages. So the contact network is kind of the initial probabilistic distribution. How you pick who's infected at time 0 is dependent on the contact network. The transmission history is dependent on those. So on and so forth. You can read more about our framework in our recent preprint. But then the question comes about of, how do we actually model these individual processes? What is the probabilistic distribution from which we should sample? So for example, with the social contacts, there's very different types of communities in which HIV is rampant. So how do these different communities have different contact network structures? For how do we pick the people infected at time 0 of our simulation, maybe properties about the demographics of the individual should have some impact as to who is likely infected. For the actual epidemic itself, how do we mathematically model the epidemic? So currently in our studies, we use a Markov process model that I can explain in detail offline. But even then, how do we denote what rates should exist? How do we learn the parameters of these rates from real data? Then there's this issue of, okay, given the epidemic, how do we model the clinical sampling? So not everyone comes to the clinic. So how do we see which individuals are more likely to come to the clinic? What is the delay between their initial infection diagnosis time? What time after diagnosis are they going to come to the clinic? How do we subsample people? So on and so forth. And then for the phylogenetic evolution, we have issues of, what types of models should we use for this? Should we use coalescent models? What should the population size function be? For example, with HIV, we typically assume there's a bottleneck effect. So we would expect some type of population growth. Do we use forward models like Ewell? What rates do we use? And given a phylogeny in unit of time, how do we actually put mutation rates on this tree? So how do we model the expected per site number of mutations per time? We can, for example, sample rates independently for each branch. That's what a lot of people are commonly doing nowadays. But how do we pick the distribution to use? Or perhaps we should use some autocorrelated model of mutation rate where the mutation rate at the current time is dependent on the mutation rate of the previous time. So maybe like mutation rate grows over time and then decreases over time. And then with HIV, they've noticed that there's significantly different rates of inter-host versus intra-host mutation rate. So they actually see relatively low diversity across patients, but then within a patient, they see very high diversity of the virus. So how can we capture these as well? And then once you have the tree and unit of mutation rate, how can we model the actual sequence evolution? Do we use the GTR model? Do we want to impose like gamma site rate heterogeneity, invariant sites? Can we model evolutionary constraints using some type of a codon model? Can we capture drug-resistant mutations, selection from the immune system, coevolution? Some people hypothesize that HIV virus, as it evolves, it actually over time reverts back to your initial infecting sequence. So can we try to model this type of a theory? Basically, a lot of open questions as far as the modeling goes as well. So to kind of end, I want to summarize some big questions we have that I talked about. Can we infer phylogenies in transmission networks? Can we use what we infer to predict future transmission events and predict who's the most at-risk demographics? Can we mathematically model and simulate realistic data sets? And for each of these points, work has already been done, but there's significant room for improvement. So I'd like to thank some of my collaborators that I work on, my advisor and 2 collaborators. And if you have any questions, feel free to ask, and feel free to check out some of the work that we've done. Thank you.
Are there any questions? Yes, please.
So I'm not a virus person, but you said that it has different mutation rates, intra-host and inter-host. Can you,
Right.
can you talk
Yeah,
about
sure.
that?
So basically, I'll say it in terms of one of the theories. I'm not sure if this theory is actually correct, but it's believed that perhaps HIV, for some reason, certain sequence features are very successful at infecting and invading the immune system. But then once the virus does an infection, it kind of has to disperse significantly across your body to be able to avoid your immune system. So it's thought that the viral sequences that actually can successfully infect individuals should have certain properties that are maintained, which would suggest low inter-host variation at the time of infection. But then within your body, if you were to sample multiple viral lineages of a given person using next generation sequencing, because of this rapid diversification to avoid your immune system in this cat and mouse game, you would expect higher mutation rates potentially. If that makes sense, yeah. So it's largely evolutionarily constrained by immune system.
I have a quick question. You mentioned the art treatment.
Yeah.
What's the main effect of treatment?
So antiretroviral therapy. So unfortunately, once HIV is a retrovirus. Once it integrates into your genome, you can't really remove it, as far as we know. But at least with these antiretroviral therapies, you can basically stop the way that the RNA polymerase replicates, and you can stop how it integrates back into the genome. So you can basically lower the viral load within your body. You can't eradicate it completely, but you can at least lessen how much virus is present.
Yeah. So what do you see that's different from the tree with or without the treatment?
Oh, with or without treatment. Well, so if you have the treatment, you actually shouldn't have any virus detectable. So it would basically, in my case, I think it would affect the population size function. So if you had some coalescent model with dynamic population rate, I think at the times that a given individual has treatment, you would expect basically a bottleneck effect. And then at the time that they stop treatment, you would expect growth again. We haven't investigated too thoroughly, but hopefully future work will do that. Yeah.
Let's thank our speaker again.